So, for the longest time in the world of language AI, you were kind of stuck between a rock and a hard place. You had to make this tough choice. On one hand, you could have a model that was super elegant, really principled, but it could only see half the story. Or you could go with a model that saw everything, but it had to use these, let's call them clever but kind of clunky tricks, like playing hide and seek with words. It worked, for sure, but it wasn't pretty. You basically had to pick your poison. Well, that was the case until one model came along and just completely changed the game. Okay, so here's the game plan. We're going to start with that big dilemma I just mentioned, the one everyone was wrestling with. Then we'll get to that incredible aha moment that just shattered the whole problem. We'll look at the clever fix that made it all possible, see how it stacked up against its biggest competitor, and then I'll give you a super simple cheat sheet to wrap it all up. Sound good? Let's do it. All right, section 1, the big dilemma. To really get why XLNet was such a huge deal, we have to understand this fundamental tug-of-war that was going on. It really was like a tale of two competing models, two totally different ways of thinking. Okay, so on one side, you've got your autoregressive models. Think GPT. These guys are elegant, right? They just learn to predict the next word in a sentence, reading from left to right. Super simple. But here's the catch. They can only look backward. It's like they're driving a car but can only use the rearview mirror. They're basically half blind to what's coming. Then, on the other side, you have the autoencoding models, and the big one here is, of course, BERT. Now, BERT's superpower was that it could see in both directions. It had the full context. But the way it did this was by, well, poking holes in the sentence with these artificial mask tokens, and then trying to guess what was missing. This created a couple of big problems. First, that mask thing doesn't exist in the real world, so you get this weird mismatch between training and actual use. And second, it forced BERT to assume that each missing word was its own little independent puzzle, but that's not how language works. Think about New York. New and York are totally dependent on each other. BERT kind of struggled to see that deep connection, and that was its big flaw. So yeah, that was the standoff. You either got the principled but half-blind model, or the powerful but kinda messy one. The researchers behind XLNet saw this and were basically like, nope, there has to be a better way. And the solution they came up with, oh man, it was a total aha moment. They asked a question that seems so simple in hindsight, but was absolutely revolutionary. What if a model could learn from text in every possible order? Now, hold on, this is the crucial part. They didn't mean scrambling the sentence itself. The sentence stays the same. What they wanted to scramble was the order in which the model predicts the words. Just think about that for a second. What would that even do? And this big idea has a name: permutation language modeling. Okay, the super technical definition is about maximizing the expected log likelihood over all possible permutations, which, yeah, sounds like a mouthful. But all it really means is that the model's goal is to get incredibly good at predicting a sentence, no matter what random order you ask it to predict the words in. So again, the sentence, New York is a city, always stays put. But what changes is the game. Maybe one time the model has to predict York first, using the other words as clues. The next time, maybe it has to predict is. It's a whole new way to learn. And this is where it all clicks. Look at all those different arrows. Each one is a different random order that the model is learning from. And the result? Over millions of these little games, the model naturally learns to connect every single word to every other word in the sentence. It effectively becomes bidirectional, just like BERT. But, and this is the genius part, it does it in a totally natural, autoregressive way. No mask tokens, no clunky workarounds. It just gets the best of both worlds. Okay, so this permutation idea sounds amazing, right? But it creates a huge, tricky, new problem. I mean, if you're trying to predict a word at a specific spot, how do you do that without just peeking at the answer? It feels like a paradox. So how did they pull it off? But wait a second. You might be thinking, how does the model even know where to predict a word without seeing the word itself? And that is an excellent question, because think about it. If I tell the model, hey, predict the word at position 4, I have to give it the information about position 4. But if I also give it the actual word that's sitting there, well, the model's just going to copy it. The game's too easy. It's basically cheating. So how on earth do you solve that? Well, the solution is just as clever as the problem. It's an architectural fix called two-stream self-attention. The big idea is that one stream of information just isn't enough to pull this off. You need two running in parallel, and each one has a very, very specific job to do. And here's how it works. You have two streams. First is the content stream. This is pretty standard stuff. It gets to see everything, the full sentence, all the words in context. It knows the content. But then you have the query stream, and this is the secret sauce. The query stream knows the position it's supposed to predict. And here's the trick. It is completely blind to the actual word at that position. It knows where, but not what. This setup forces the model to use all the other words as clues to make its guess, and it makes it impossible to cheat. So clever. All right, section 4, the showdown. The theory's beautiful, right? This whole permutation thing, the two-stream attention to make it work, it's all so elegant. But the real question is, does it actually work? Does it beat the reigning champ, BERT? Let's find out. Okay, let's take a really simple phrase to see the difference in action. New York is a city. Imagine we've blanked out the first two words, and the model has to figure them out. So with BERT, because it's trying to predict both masked words at the same time, it treats them as two separate puzzles. It's trying to guess new and trying to guess York independently. It misses that obvious critical connection between the two words. But XLNet, because it predicts words in a sequence, can actually learn that dependency. It might predict new first. Then it takes that new piece of information, the word new, and uses it as context to predict the next word. And of course, once it knows the first word is new, predicting York becomes a whole lot easier. It captures that vital connection. And guess what? This isn't just theory. This advantage shows up in the results. Big time. When you train both models on the exact same data, so it's a fair fight, XLNet consistently outperformed BERT on a whole bunch of important benchmarks. I mean, just look at these numbers. It's a clear win. The win on the race dataset was especially impressive. That's a 2.3% improvement. And this is probably because race involves reading really long passages of text. And remember, XLNet had another trick up its sleeve. It was built on top of Transformer XL, an architecture that's just way better at handling those super long contexts. Okay, that was a lot, I know. So let's wrap it up and put it all into a simple cheat sheet, so you have the key takeaways right here. Now, it's really important to be honest about the limits here. The creators of XLNet were super upfront about this. This new permutation method is not a free lunch. It's a way more challenging and complex task for the model to learn, which means training can actually be slower. Plus, to even make it possible to train, it doesn't predict every word in every step, just a fraction of them. It's a trade-off. So, if you're going to remember anything from all of this, let it be these 4 things. 1. The goal was to get the best of both worlds, AR and AE models. 2. The big idea to get there was permutation language modeling, shuffling the prediction order. 3. The clever trick that made it work was two-stream attention to stop the model from cheating. And 4. It was all built on Transformer XL, which made it great at handling long text. That's the whole story in a nutshell. Ultimately, XLNet was so powerful because it challenged a fundamental assumption everyone was making back in 2019. And that leaves us with a pretty cool question to chew on. What's the next big assumption we're all making right now that's just waiting to be rethought? What's the next permutation moment? This video is generated with Google's Notebook LM, based on cited resources and for reference only. I really encourage you to take this further. I'm genuinely excited to see what you discover. If you have topics you'd like me to cover, drop them in the comments, leave a rating, and please subscribe if you enjoyed this. Thanks so much for watching. Until next time.